so now we know how to find a QR factorization of a matrix. You remember the last section where we said that if we have a matrix with orthonormal columns, the least squares problem was easy. So if A has orthonormal columns and we want to find a least squares solution to AX equals B, then all we have to do is X hat in this case would be just A transpose B. It's that easy. Orthonormal columns. Well, what if A does not have orthonormal columns? Well, if we can find a QR factorization of it, we then have a Q that does have orthonormal columns. And that means that we can actually get not as nice of a solution, but we can actually get a nicer solution than we had before. So let's say that we have AX equals B. We want to find a least squares solution, but we also know a QR factorization A equals QR. Well, we took this when we did the least squares problem. We took this and we turned it into what we called the normal formulas or normal equations, which were A transpose AX equals A transpose B. If we replace A with QR, this becomes QR transpose times QR X equals QR transpose B. Remember, the transpose of a product is the product of transposes in the reverse order. And now we have two things that happen. First of all, because we're assuming here that A has rank n, where it's m by n, then R is an invertible matrix. That means R transpose is invertible. So we can actually cancel that out. We can get rid of the R's. We don't need, or the R transposes. We don't need them. Secondly, Q transpose Q, because Q has orthonormal columns, Q transpose Q is the identity matrix. So actually this part is the identity. That's the identity. So really our equation is Rx equals Q transpose B. Or since we're dealing with the least squares solution, maybe we'll call that X hat. But what do we have here? We have a different system of equations. So Q transpose B is a column vector. But the important thing is that R is a non-singular matrix. So we can actually solve this. In fact, if we wanted to, we could go ahead and just say this is R, that X hat is R inverse Q transpose B. But we're kind of missing the point here if we do that. R is not only non-singular, it's also upper triangular. So if we wanted to set this system of equations up as an augmented matrix, we don't have to do any row operations. Those are already taken care of. Our augmented matrix would look something like we have a bunch of zeros down here. We have other numbers in these places. That's okay. And then we have our column here. But we can easily do a back substitution. We can immediately get whatever is our solution for this last number. We can use that to find the next one, and so on and so forth, going all the way back up. We don't have to do any row operations. They're already taken care of once we have this form. So rather than try to find some inverse, which is kind of annoying to have to do, we can just use back substitution and save ourselves a ton of work. So let's actually do that in some of the problems we've already worked on. So going back to problem 6, we started with this matrix A. It was a 3 by 2 matrix. We turned it into, well, we found the Q and R, the QR factorization. So A is the product of Q and R. And they gave us a vector B. And we wanted to solve the least squares problem AX equals B. Let's actually do that. So what do we need to do? Well, all we need to do is take Q transpose times B. So let's actually write that out. Our first row is 3/5, 4/5, 0. Then we have a negative 4 over 5 square root 2, a 3 over 5 square root 2, and a 1 over square root 2. And that's going to be multiplied to 0, 20, 10. So remember, we're doing row by column. So actually we have a 0 plus 4/5 times 20 plus 0. Well, 4/5 times 20 is going to be 16. Next one is going to be a little bit more complicated. Let's kind of ignore the square root of 2 parts because that's just going to be on the bottom anyways. So we have negative 4/5 times 0. We have a 3/5 times 20. We have a 1 times 10. 3/5 times 20 is going to be a 12 plus 10. It's going to be a 22. So if we take 22 and we divide it by a square root of 2, let's rationalize that. We can basically turn 2 over square root 2 into just a square root 2. So we ultimately get 11 square root 2 as our solution. Or not our solution, our this entry. And what's that saying? Well, we have R times our least squares solution is equal to Q transpose B. Let's just put our R as the first part of an augmented matrix, and the Q transpose B that we just calculated as the second part. And now we can just solve it. Our second equation, let's just use x and y instead of x1 and x2, but this is saying that 2 square root 2 times y is equal to 11 square root 2. Well, the square root 2's really don't matter here, so we can go ahead and divide and get y is 11 halves. Then we use that for the other part. We have 5x plus y is equal to 16. If y is 11 over 2, what do we get? We get that x is 21 over 10. So our least squares solution is 21 over 10 and 11 halves. And that's all there is to it. Once we have this QR factorization, it makes solving this least squares problem really simple. We don't have to take some inverse or anything like that. We're done. Just a back substitution gets us there. Let's take the first matrix that we did, that we found a QR factorization for. So this was at the beginning of the last video. And we found Q and R to be these things. Let's go ahead and let's pick a vector B. Let's just say 4, 4, 4, 4. 4 is there just to make the numbers come out nicely. But we want to find the least squares solution to AX equals B. How do we do that? Well, same process. We're going to take Q transpose times B. So here, maybe I won't write it out, but keep in mind we're essentially taking the columns of Q times the column B, and those will be the entries in our column. So we have three columns of Q. That will be the 3 rows of our product. Our first one, we take all of these, we multiply them by 4, and then we add them together. Or you could just factor out the 4, I guess, and just add these together and then multiply the result by 4. If you add these together, well, something kind of interesting happens here. We have this is that, but this one's negative, this one's that, but this one's negative, so they cancel each other out. You get a 0 there. So, got rid of the square root of 2's. Wanted to not have to deal with those. Other ones won't come out to be zeros. So we're going to take second column of Q times B. We have, well, again, we can just add these up and multiply the result by 4. So 2/5 plus 1/5 plus 4/5 minus 2/5. We actually get because the 2/5 cancel each other out, we end up getting a 5/5 or 1, and we multiply that by 4 to get 4. And then we can do the same thing here. Again, we get 4. So, very nice Q transpose B. Not always going to be that nice, but wanted to make it easier on us. Not that this would be that complicated either way, but it is quite a bit of writing. Now we're going to remember that we have R times X hat is equal to Q transpose B. Our R we're going to put here as 5 square root 2, square root 2, negative 6 over 5 square root 2, 0, 0, 0, 1, negative 4/5, 4/5. And our Q transpose B is 0, 4, 4. Alright, so what does this mean? Well, our first equation is, well, not first equation, the last equation, first one that we're going to work with, is 4/5 times z is equal to 4. So what is z? Z has to be 5. Easy enough. Second equation, and second equation we're going to be working with, is y minus 4/5 times z, which is 5, so that's going to be a 4 here, is equal to 4. So y minus 4 is 4, so y has to be 8. Finally, we have 5 square root 2 times x plus square root 2 times y minus 6 over 5 square root 2 z is equal to 0. If we actually multiply everything by square root of 2, this becomes a 10 because the 2 square root 2's will become a 2. This becomes a 2, and here the square root of 2 on the bottom will cancel out, and well, I'll just leave it as 6 over 5 for the moment, but multiply by z. We stick in our numbers, so we know that z is 5, so this will be a 6 here. Y is 8, so this will be a 16. So 10x plus 16 minus 6 is equal to 0. In other words, x is going to equal negative 1. So our least squares solution is negative 1, 8, 5. So obviously a lot of work went into finding that QR factorization, all that orthogonalization. And maybe you could say, well, in this case, maybe it would have been easier to find that least squares solution directly by the process that we used before. But this actually can get a lot easier the bigger you go. And finding the QR factorization is actually, because we have this very nice Gram-Schmidt process that we don't really even have to think about, we just kind of plug in numbers and go, it's actually something that's really handy for computers to be able to do. So this is how you might program a computer to actually solve least squares problems, rather than having to have it find inverses, which can be actually a little not tricky per se, but actually can cause some issues with rounding, stuff like that. This is actually a much more robust way to do that. The book actually gets into a lot of that kind of stuff, where the Gram-Schmidt process can actually be improved. There's a modified Gram-Schmidt process that's even better for doing it on a computer. You can get better results just because of the whole rounding issue. There's actually even better um, processes for computers that the book actually talks about in, I think it's in chapter 7. We're not going to get into that in this class, but that's well, when we kind of in the subject of numerical linear algebra. Um, Getting way off topic here, but the point here is that being able to do all this orthogonalization, all these QR factorizations, these are things that you would do with a computer, or a computer would be doing at least in the background of solving all these different types of problems. So, kind of giving you a glimpse into how this is all done, not necessarily by hand, but by a computer. But that's all I really had to say for it here. I'm sorry this section had a lot of video to it, but the problems just are fairly lengthy. They actually do take some time to go through. And I wanted to make sure that we had plenty of examples of how this works. So I'll leave it there, and I'll see you in the next chapter because we are not going to be covering 5.7. Actually, we kind of covered it a little bit in this section, but we're not going to cover it separately, and we're not going to have any problems over it. So I'll see you. The next video will be 6.1. So, goodbye.